right now and turn it over to Lejo.
Awesome. Thank you, Ryan, for that introduction. And thanks, everybody, for coming today. I'm thrilled to be here with you today. And I just want to attest as well, the tools that have been developed under the Pangeo initiative and the contributions that have been made have really been transformative for our research group. And it's made some of the analysis of a lot of the data sets that we produce just so much more straightforward, easy, reproducible, enables so much more kind of peer-to-peer mentoring to disseminate that knowledge. And so I want to first start off by saying thank you all. And I look forward to further integrating myself with the Pangeo community over time. And the project that I'm going to talk about today is really what I view kind of my opportunity to sort of further onboard and integrate myself. So I look forward to seeing you all more in the future as well. And so today, what I want to do is really start off by I got some really good advice at some point, which is like start off your slides, your slide deck with the conclusions of your talk, and I really liked that. So I'm gonna start with kind of the conclusions or the big picture takeaways of this talk, because I think they inform the rest of the talk itself. And just as a heads up, there's not a lot of there's only maybe one slide of kind of scientific results in this. It's really kind of a forward-looking talk about kind of the direction that I see sort of my very narrow niche of hydrology and computational hydrology going. And a lot of that is informed by where I sit as an educator, and where I sit as somebody who I think, being at a state university, part of my role is in bringing that science and ensuring that that science is of use to the stakeholders in this state and elsewhere that actually manage water resources and make day-to-day decisions on the things that affect us. And at the very end of this talk, I'll open maybe some questions, and maybe that can provoke some discussion, and see what thoughts folks have about how we can sort of connect those kind of those multifaceted missions that we have. So um, from my perspective, I think, what I've been seeing in the past year, and I think a lot of this is not going to come as any news to anybody on this call, right, is that um, cloud computing is just increasingly important in computational earth and environmental science. And I really think that it's only, going to become more important through time. A lot of this is of necessity. The size of the data sets being generated by initiatives like, the CMIP6 and onward, the size of those data sets, the size of the data sets that are collected by NASA. I was actually just talking to a friend and colleague at Goddard Space Flight Center today. NASA going forward, their Earth science data is going to be in the cloud. The size of the data sets really can't be handled by the kind of storage capabilities we have at our academic institutions, or even by organizations like the National Science Foundation or NSF. And so the commercial cloud, or the cloud more broadly, is just kind of going to become an increasing thing that we all need to leverage for our research. Um, at the same time, because of this, many hydrologic modeling workflows and user cases fit well in a cloud computing model. And that's becoming even more apparent as a lot of the data that we need as input to our models is stored in the cloud. And at the same time, just the diversity of the computational resources that are available to us. There is a scale and diversity of computing capabilities that is out there in the cloud, that sort of is far beyond what a Boise State or any university can sort of provide. And so in a lot of ways, the cloud potentially provides us this opportunity to create sort of fit for purpose computational solutions, that that target our specific applications and are only only built for those things that we need to do as scientists. Um, and this is just sort of playing to the crowd at this point, but open and reproducible computing tools can bring computational research and decision making closer together. And the hope of that vision is that ultimately the research that we're doing is getting in the hands of people that are making decisions and helping support the knowledge, information, and data gaps that people have as we both try to mitigate climate change and try to adapt to its impacts. But there's an urgent need for effective training and onboarding, right? And so this is kind of the space that my head is in quite a bit, and I know that a lot of you are sort of in this headspace as well, right? That there's all these things that we know we probably need to be doing, and right now we're sort of only catching up when it comes to developing the effective training practices to use these tools to realize this vision of kind of end-to-end um, end-to-end and open and reproducible science, where our basic research is rapidly getting in the hands of the people that are making management and policy decisions. So this happened just kind of by happenstance. So last year, NSF created this new mid-career advancement program. And I saw this and I was like, well, that's interesting. What would I do for this? And this is taken directly from the solicitation. So the mid-career advancement program, seeks projects that envision new insights on existing problems or identify new but related problems previously inaccessible without new methodology or expertise. And so I said, okay, well, this is actually a real opportunity to level myself up, right? To devote some time and effort to getting myself back up to speed in cloud computing in a way that will affect the long-term trajectory of my own individual research, but also hopefully my role as an educator and my role as somebody who is seeking to bring research insights to the managers and decision makers in my region. And so I developed a proposal and submitted it. I was very fortunate to actually get it funded, and the rest of this talk is devoted to what this project is about. If you're interested in this proposal, feel free to contact me. I actually will probably at some point put it up on Zenodo and list it on Open Grants, but until I have the time to do that, let me know. I'm more than happy to give you the proposal and give any feedbacks on ideas and thoughts. It's a little bit of a different proposal from NSF's perspective. So and the motivation of this project is very much tied to kind of my own personal historical training and what I would call kind of the legacy modeling workflow, right? This is what I was trained as. This is the and I'm using workflow very loosely here. This is kind of just what we did as graduate students and as postdocs and early in my career, right? It involved acquiring, and I intentionally used here the oldest icons I could find. So we would acquire some data. Sometimes that would literally mean, getting a physical hard drive in the mail, right? That data maybe came off of a tape drive somewhere, or we would download it probably through an FTP site. We might even have to sort of right click, to download it. We would acquire that data. We would run our model, usually using kind of an on-premises machine that was maybe even on our desktop, or if we were lucky, kind of in a room that stored a small cluster to be able to run these models. And then we would write a paper, and there maybe would be some line in it that would say something like the data is available on request to the authors, right? And that, come on, we can do better than that. And so just in part by kind of being aware of you all's work and knowing Ryan and others on this call and in discussions, I started to see kind of the building blocks of a newer and what I would argue is better model, right? So there are all of these tools that are out there. There's all of this data that's hosted in the cloud, the CMIP data, the NASA data I've mentioned before. It's going to be there. It's in buckets. The storage mechanisms, the data structures, the data models for how that data is stored is getting better. Um, there's all of these cloud computing tools, right? And they're getting easier to use. There's a diversity of options out there. GCP, AWS, and Azure are the kind of most common. So it's a competitive market. There's also sort of resellers for better and for worse that will sort of help connect you with those resources. Um, and that what they offer is increasingly sophisticated, right? So it meets or exceeds the capabilities that we have on premises. And at the same time, we can store whatever data. It never has to leave the cloud. So there might be no need to actually sort of bring that data back on premises. We can use tools that are out there, things like Jupyter Hub, Pangeo. Um, we can use those tools to do the data analysis we need to do in the cloud online, and we can use other initiatives like Kuazi's HydroShare to make that data, those workflows, visible and transparent to other users, be they other researchers that are out there, graduate students, or potentially those decision makers and practitioners and managers that we're seeking to meet. So and just as an illustration of this, I think that the future is very much open, right? So those that aren't hydrologists, um, this is true in other sciences, but hydrology is often a very kind of local science, right? We are very much interested in our own backyard, right? We're interested in understanding the impacts of climate change to the hydrologic response in Idaho, in the Snake River Basin, for instance, right? And so the tools to illustrate, how the tools that are out there are becoming more and more available to support these kinds of workflows. I have this slide here, which sort of illustrates that, for instance, Kuazi has worked with the folks that developed the National Water Model, Dave Gotches's group at the National Center for Atmospheric Research, as well as in support of an SF-funded project called the HydroFrame Project that I'm fortunate to be a PI on, to provide these domain subsetters, right? So a very common workflow or use case in hydrology is something like this. Hey, I know and appreciate that you have developed this continental scale model, but what I really want to do is use a cookie cutter of the Snake River Basin, and bring my own forcing data, bring my own land cover data sets, bring some additional value to the model that's already been set up there. And I want to run that model and make an improvement over that Kona scale model for our neck of the woods. And I want to be able to speak to the folks at Idaho Department of Water Resources, the Bureau of Reclamation, and other actionable agencies about what is over the horizon and what are the ramifications for some of the impacts that we're already seeing in the Snake River Basin and in its sub watersheds that are in our backyard. So it's tools and workflows like this that are making it much easier to to bring value and to add value to what's already being done at larger spatial and sort of larger scales of perspective. And I think that that's a really fascinating and big increment, and it's a big event that is allowing us to kind of push our applications forward. So the proposal was actually sort of centered on user perspectives, and so Um, you know, I developed this proposal in part by envisioning, three different users: a modeler, a water data scientist, and somebody who's generating large data sets that they would like to share and disseminate and ensure that there's visibility and usability and reproducibility of that data. Oops, sorry. There we go. Um, and around that, I developed specific both research objectives. So, what is the actual research that I'm trying to do in this project? But in addition to that, what are the educational objectives associated with each of these users, right? So, we are looking at doing some very specific science in this project, as well as developing the educational materials and training to be able to then propagate that knowledge that was generated by doing the research into the educational sphere, right? To make sure that our students are equipped and have the knowledge and skills and capacities to be able to do some of these cloud computing tasks for the purpose of their own research, but also for their own professional developments, right? So the hope here is that by equipping students with some of these skills and training, that they ultimately go to work for some of these agencies and are bringing some of that knowledge and capability to their future employment environment, right? So students that go, have some cloud computing capability and go to Idaho Department of Water Resources, when they need to spin up a significant computational resource, it's no longer kind of a large capital investment that IDWR was never going to make to begin with, but is now a question of like, okay, well, we can create this fit for purpose computational solution in the cloud that will allow us to do this very specific task, right? So that's kind of the motivation and the vision behind the educational objectives. So we're going to learn by doing, right? So this is kind of the wiring diagram that's behind the project. The idea was to create a large ensemble of hydrologic projections in the Snake River Basin, basically only in the cloud, right? Doing as much of this in the cloud as we possibly can. So using the CESM large ensemble as the inputs to primarily the intermediate complexity atmospheric model that Ethan Gutman has developed at NCAR, as well as a single WRF model run. This is kind of the biggest probably computational task that we have in the cloud. Using those to force the WRF hydro model, and then using the outputs or storing the outputs or some subset of the outputs that are, what we're primarily interested in as hydrologists in the cloud, being able to analyze that using things like a Jupyter Hub instance, but then using that Jupyter Hub instance to then allow others that might be in agencies and organizations that are doing management and decision making to see that data and to be able to use it and analyze it for their own purposes, right? And these align with each of these kind of user experiences, right? So there's a modeler, there's somebody who's doing the data analysis of a large data set, and there's somebody that's wanting to share that data via the cloud. So that's kind of an overarching view of the project. It's more detailed than that, obviously, but I didn't want to spend too much time on sort of the details of the research. What I do kind of want to do as I pivot towards kind of the end of this talk, right, is think about, well, how can this help us add value for our stakeholders? And the best model I'm thinking about here, right, is as kind of like what in business they talk about as kind of being the value stick, right? And so I think about, those folks that are originators of data, developers of these models and algorithms, be they things like WRF Hydro or kind of new, AI, ML algorithms. Those folks are kind of the originators of these data sets and models. And where we come in, right, we add value by bringing we're basic and applied researchers, and we add local context or perspective through additional modeling, additional analysis, or just interpretation of that data set. And ultimately, at the sort of the top of the value stick is kind of those managers and decision makers that may have knowledge, information, and data gaps to support those decisions and the making and implementation of policy. And so, really, kind of the last mile problem here is really us, right, in that kind of basic and applied research space, whose job it is to kind of ensure that we're doing things in a way that's transparent, open, and reproducible, that we're using this originated data effectively, that people know how we use that data, what assumptions we are making in using that data, and what its limitations might be. But also at the other end of the value stick, in that interface with managers and decision makers, to make sure that we know what their knowledge, information, and data gaps are. We are doing effective stakeholder engagement to ensure that, as we kind of do our modeling, analysis, and interpretation, it's done so with the end uses of those decision makers and policymakers in mind. So beyond this project, and this is the point where I would love some thoughts or discussion, and I know you all are sort of thinking about these things, but how do we integrate these training opportunities into our existing curricula, right? And what are innovative ways to share training across institutions? I'm now participating in the Kawasi Virtual University, which is a potentially excellent model for being able to provide specialized but bite-sized knowledge and training across multiple institutions. And then additionally, how do we extend this training and workforce development to partners at management agencies, right? What is our role as educators in, helping to retrain and, do some, I can't remember what the higher ed admin folks call it, but reskilling or upskilling, I guess is what it's called, of folks that are already in those agencies and organizations. So that's a big thing that I don't necessarily have the answer to, but I think is a really important question for us now and in the near future. The last thing that I wanted to mention is just the broadening participation aspect. I'm super psyched about this. This isn't necessarily a cloud thing, but I think it's going to be fun. There's a containerized version of WARF for Raspberry Pis. And so the broader impacts part of this grant actually will work with some teachers in the Nampa School District, which is just west here in of Boise. It's about 45% non-white population, so it's actually a very diverse school district. And the goal is to provide a research experience for teachers where they will get a stipend over the summer and some help with me to get a version of WARF, a reduced complexity version of WARF, up and running on a Raspberry Pi, so that they can be making forecasts for our local neighborhood, basically, in the classroom with the students, right? And so their goal will be to develop some of the curriculum, and my goal will be to support them in the sort of technological development and making sure that the students understand the skills that come along with the earth sciences, right? Underscoring that earth sciences does provide you with a set of very marketable skills, and trying to get at that at sort of that eighth grade or junior high level, when students really start sort of cognating about what their future might look like. So with that, thank you so much for this opportunity to chat with you. I'd love some thoughts and insights into what you all think the future is. So thank you.